Log on, tune in, find out. Another good idea from Cambridge.
So thank you. First, I'd like to thank the organizer for giving me the opportunity to speak in this nice conference in this beautiful mathematical center in Cambridge. The title of my talk is on exact optimal sampling designs for processes with a product covariance structure. So this will have some common points with the previous talk of Anatoly, but the difference, just to highlight the difference, is that we will talk about exact sampling designs for a given number of observations, but that would make things more difficult, of course. But to make things simpler, we will only consider so-called product covariance structures. My name is Radoslav Harman, and I'm from Comenius University in Bratislava. So, firstly, let me give you outline of the talk. I will discuss only about models, or mainly about models with one-dimensional parameter. So in this hierarchy of Anatoly's models with increasing level of difficulty, we will talk about the second one. Not the first one, but the second one. I will also make some remarks, depending on how the time will allow us, about a multidimensional case, about the third in that hierarchy. Then I will talk a little bit about product covariance structures. So which examples do we have of product covariance functions, and what are the basic properties of product covariance functions? And then we will switch to design. We will talk about something which I call exact regular optimal designs with prescribed initial and the final design points, if we look at it, the design space as time. It turns out that it's better to separate, in this context, it's better to separate two tasks. First, to find optimal designs with prescribed beginning and end design point, first and the last design point, and then try to maximize the information with respect to moving the beginning and the end point of the experimental domain. The information about the parameter. In this talk, the information will be a scalar value. We, of course, need to only maximize information of a single parameter or minimize variance of the single parameter. It's the same. So we will not talk about any criteria of optimality. We do not work with information matrices in this talk, just with simple information. So we will skip this. Why do we do it? Because the ideas that I would like to present are already here in this simple case of one-parametric models. Of course, then they can be formulated for multidimensional space. I mean, the space with multidimensional parameter, the models with multidimensional parameter. But just to present the ideas, it's enough to consider one-parametric models. Then there's something that I call the Wiener equivalence theorem. We'll show that the Wiener product covariance structure, which is the simplest one among all product covariance structures, can be taken as canonical. If we solve all problems, all design problems for the Wiener covariance structure, then we solve all problems for all product covariance structures, as we will show. Then we will talk something about the Wiener covariance function and about some result of existence and similar results of existence of optimal designs, of optimal regular designs. And then we switch to specific models that I call parabolic, square root, and hyperbolic class of regression functions. It turns out that for these three classes of models, we can indeed obtain a simple, exact endpoint optimal designs. Okay? No more classes that I would found, but for these three, the results are very simple. Then we will talk about something that I named nested optimal designs. That is connected to the function A that Anatoly used, that is usually used for constructing asymptotic designs. we will require that our sequence of exact optimal designs can be constructed using such a function A. We'll see it. And then something about ultimate efficiency. What is an ultimate efficiency? As was already remarked, the information that we gain is limited, usually in correlated case, is limited by a finite value. In other words, even observing the full trajectory of the process, we do not have an estimator of the parameter, the variance of which would go to 0. The variance is limited by a non-zero value. And ultimate efficiency is the efficiency of a given design compared to what we could achieve by observing full trajectory of the process. And then we can say something about the case of a multi-dimensional parameter. Okay, so let us be more formal. Assume a random process yt, where t belongs to an interval ab. A can be minus infinity and b can be plus infinity, defined by the following formula. So the second Anatoly's model. We will assume that beta is one-dimensional unknown parameter of interest, which is to be estimated from observation of the process in a finite number of times in n time points, chosen in n optimal way, we'll specify it later, within a given experimental domain, which is under this interval a, b, and it will be, in our case, just an interval including the boundary points. F is a known continuously differentiable function that I will call regression function, because of course this will turn out to be under specific design a regression model, with at most 2 roots on a, b. This is just a technical point to formulate some smooth mathematically neat results without just some exceptions. Epsilon t is a Gaussian random process of errors with a zero mean value function and the covariance function rst. We will assume that this covariance function is of very specific form. That is the so-called product covariance function. That is, there exist functions u, v defined on the interval a, b, such that rst can be written in this form for s less or equal to t. Of course, it must be symmetric, so by this it is also defined for switch values. This model will be denoted by f, u, and v. So these product covariance functions have been used in the context of optimal design in several papers already. It was noted that these product covariance functions lead to simpler formulas. Already in this famous paper of Sachs and Ylvisaker in 1966, which exactly deals with this problem of one parametric model, similarly as we do, there are some examples calculated for this product covariance structure, but these are asymptotic examples, not exact, and not for the classes of mean value functions or regression functions that we do consider. There's another paper in Canadian Journal of Statistics which is called Exactly Optimal Sampling Designs for Processes with a Product Covariance Structure, very similar as the title of this talk, but the aim of this paper is different. The author assumes that the mean value is constantly 0, and the aim is prediction of the process. Okay? Of course, we can have two very natural aims. The aim that we consider here is estimation of the parameter beta, but another completely valid and natural aim would be to predict the process in a point, or predict in all points in some sense, for example, do some criterion of integrated mean square error and so on of the predictor. But this paper considers only processes with zero mean value function, not beta ft as we do. And there's another paper that already contains some formulas that I will present. The paper or the results were presented in the St. Petersburg workshop on simulation in 2009, organized by Radoslav. what are these assumptions? To make it mathematically simple, we can use some assumptions on the functions u and v. They are positive on AB. It's natural that we require them to be positive on AB. And there is one very special function that is related, that is strongly related to this product covariance functions, and it's the ratio of the two functions u and v. Okay, so u divided by v. We will denote it by r, so this is a function r defined on the interval AB, and we will assume that it is increasing on interval AB. In all the examples that I'll show, this function is indeed increasing. We will also require that the limit of this function r with s goes to a from right is 0, and if t goes to b from left, then this limit of the function r is infinity. It then implies some nice behavior of correlation function between 2 points. Here we have a following simple lemma. Let sigma be a symmetric matrix of type n times n with the following entries. These are entries already made for the product covariance structures. These will occur in product covariance structures. And let these ratios of ui and vi satisfy these inequalities, which is, in a sense, the assumption that r is increasing on the interval AB. Then determinant of the matrix sigma can be written in the following very simple form. And then it is, of course, greater than 0, because this is assumed to be positive. These differences are positive, and R1 is also positive. This lemma implies that if u and v are positive on AB, then for this function u as vt to be positive semi-definite or positive definite, the definitions might differ. Simply, it defines a covariance function of a random process in a proper way. The assumption that r equals u divided by v is non-decreasing on AB is essentially sufficient and also necessary. Okay, so this assumption that the function r is increasing on AB is almost, so to say, necessary and sufficient condition for this product covariance function to be a proper covariance function. So these assumptions are not very strict. So let us look at the correlation function, correlation between two observations ys and yt. It can be written using this function r, in the following simple form. And know that for a fixed t, the correlation of s, of the process in the point s and t, is increasing as a function of s. So if we move with s to t from your view is from left, then the correlation goes increasingly to 1. And if we go to a from left with s, with fixed t, then the correlation goes to 0. Okay? And similarly, if we fix s and go with t from right to t, then the correlation goes to 1. And if we go with t to infinity, then, or to b is often infinity but not always, to b, then the correlation goes to 0. Okay, so the correlation behaves in a quite natural way. The more far apart the observations are, the less the correlation. Okay, the lower the correlation. So let us look at examples of product covariance structures. First example, well, any function r, or the couple of functions u and v such that r is increasing, defines some proper product covariance structure. But the most notable of them are the following. Wiener process. The covariance structure of the Wiener process is the following. Sigma squared s for s less or equal to t. So in this case, a and b will be 0, infinity. A will be 0, b will be infinity. So this function u w s is sigma squared s, and v w t is constantly 1. The function r is sigma squared s. Brownian bridge is another random process with a product covariance structure. The covariance function of Brownian bridge looks as follows: S times 1 minus t, with a and b the limit points 0 and 1. The function u for Brownian bridge is obviously sigma squared s, and the function v is 1 minus t. The function r is nicely increasing on the interval 0, 1, t divided by 1 minus t. Another famous covariance structure that is of product type is the Ornstein-Uhlenbeck covariance structure. So we have some constants, sigma squared lambda, and the covariance function of the Ornstein-Uhlenbeck process can be, for example, written in this form, and it decomposes to u times v if we take u to be exponential lambda s and v to be exponential minus lambda t. And again, the ratio of these two functions is a nicely exponentially increasing function, exponential of 2 lambda t. A very interesting example of covariance functions of product type has been found by my PhD student Vladimir Lacko, and it is defined by a non-autonomous Ornstein-Uhlenbeck process by this formula, by this stochastic differential equation. And it turns out that the covariance function of this process, of the process x, which is defined by this formula, by the stochastic differential equation, is of the following type. So u, we can take u to be this function, and v to be simply this function, this exponential function. And the ratio of these two would be the function r, which is the following integral. Again, of course, we should assume some very simple and natural properties about the function sigma squared. It cannot be any. But there is a vast number of proper function sigma squared, such that this function r satisfies all our preconditions that we required in the introduction. Sigma squared cannot go too quickly to 0, for example, so that the limits of r are as required. For details, you can look at the poster of Vladimir in the next room, Planning of Experiments for a Non-Autonomous Ornstein-Uhlenbeck Process. So this is a picture of some of these functions. Of course, it doesn't tell us much. This is the Wiener function, the appropriate function r for the Wiener covariance structure from the Brownian bridge. A and b here are 0 and 1. From the Ornstein-Uhlenbeck process, here a and b are minus infinity and plus infinity. And this is something that I sketched just randomly, an r function, the r function for the non-autonomous Ornstein-Uhlenbeck process. If we look once again on this formula, the function sigma squared can be almost any, and then it transfers to almost any form of the function r. So simply, for example, such function r could be obtained from this non-autonomous Ornstein-Uhlenbeck process. But what is more important is this remark over here. Note that the function r, well, it's trivial, but let us keep it in mind. The function r from ab to 0 infinity is a bijection. Okay? It's an increasing bijection. That is, there is a well-defined inverse function, r minus 1, the inverse function of r. We will use this inverse function often. Regular sampling design. So what are regular sampling designs? We assume that we can observe the process in n, which is at least 3. Okay, I won't skip the trivial cases. 3 points, design points or sampling times, chosen in the experimental domain t down, t up. Actually, it's t star down, t star up, but I call it t down and t up, or t min and t max was used. We understand what does mean. A regular endpoint sampling design on this experimental domain is any vector, any finite vector, t1 to tn, such that the first point coincides with this initial point of the experimental domain, with the left boundary of the experimental domain, and the final points coincides with the right boundary of the experimental domain. And all these other design points are strictly separated. Okay, they cannot be the same. We do not permit many observations in the same time, which is quite natural for these correlated problems. The set of endpoint regular designs on the experimental domain will be denoted by this fracture Tn. We immediately see that Tn is not compact. That is, even if our criterion that measures a quality of the design is continuous as a function of design points, an optimal regular design may not exist. It might simply try to put these design points closer and closer, and there might be no optimal regular design. So the question of existence is a valid question. It's not completely trivial. It turns out that for the design problems with a product covariance function, it is simpler to first find a method of constructing optimal designs with fixed initial and final design points, that is, with fixed initial and final design point, and then find the optimal position of the two initial and final design points as another problem. Of course, this would, if we somehow know how to construct the optimal design points between fixed initial and final design points, then to find the optimal position of the first and the last is a matter of two-dimensional optimization. It usually can be solved, or sometimes can be solved analytically, and always practically it can be solved numerically. The optimization of on two-dimensional space is very simple numerically. Of course, the original problem to find the design is an n-dimensional optimization problem, which might be, of course, very difficult, numerically even. So if we have a fixed design tau, the n-dimensional random vector of observations satisfies the linear regression model with correlated errors, this one, where f is a vector ft1 to ftn, epsilon is a random vector which has, under the assumption of Gaussian process, is a normal distribution with a zero mean value, and the regular covariance matrix sigma. That the matrix is regular follows from the lemma that I presented a couple of slides before. Under the design tau, the weighted least squares estimator of beta is the following, has the following formula, where m is the information. So here I will use the proper weighted least square estimator. Okay, so no classical least square estimator, but I will use it properly with this sigma to -1. Of course, this could be very, very difficult if I didn't assume a very simple covariance structure. But it turns out that this product covariance structure has the advantage that we can calculate this inverse quite simply. Okay, so it's a very special correlated problem in which we can calculate the inverse of the covariance function quite simply. So our information, something that tells us how much we know about beta after the observations taken according to a design tau, has the following form, which is, of course, in this case, 1 divided by the variance of the estimator, of the weighted least estimator beta hat. So it's completely natural that we would like to maximize this or minimize variance of this weighted least squares estimator. That would usually be called information matrix, but it's just 1 times 1 information matrix in this case, so I'll call it just information. A design tau star from among all regular endpoint designs is optimal for estimating beta if it maximizes this information within the class of all regular endpoint designs. It turns out that the assumption of the product covariance structure greatly simplifies some formulas, some calculations. Firstly, it simplifies any formula for bilinear form defined by the function sigma, the inverse of the covariance function sigma, and consequently calculation of the information about beta. Assume that we have a model F with a covariance structure UV on the experimental domain T down, T up, and let T be a regular design. Then the information can be written in this following very simple form. let us look at it more closely. The information is additive in a sense, similarly as in the uncorrelated case, because in a correlated case everything is very simple, and we can simply, we have a sum of some contributions of every single point. Again, we have here in the product covariance structure, again we have a sum of some contributions, but these contributions depend on a relation of two neighboring points. Okay, so this is a sum of some relations between always couples of neighboring points in the design. So the information is in a sense additive, and from this special structure we can gain much. For example, this what I call Wiener equivalence theorem. Assume model FUV, and R is our function that we repeat, that we already used for several times. And let this satisfy the assumptions from the introduction. Let us assume that T star be a regular design on this experimental domain T down, T up, and T tilde, tau tilde star, be a regular design on tau tilde down, tau tilde up, where the relation between these two designs is very simple. Simply the design points of the original design, tau star, and the design points of the implied or transformed design, tau tilde, are on the following relation. Simply they are transformed by the function R. Of course, the boundary points are also transformed by the function R. Then the following two statements are equivalent. The design tau star is an optimal design, optimal endpoint design for this model, for the original model F, U, and V on its own experimental domain. And the equivalent statement is that the design tau star tilde is optimal endpoint for another problem with another regression function, but with very simple covariance structure, precisely the Wiener covariance structure. So we can when this function, where this function f tilde is defined as follows. Okay, so simply we transform using the function r and this function v2 that is in this covariance structure. We transform the regression function f to some regression function f tilde, and the new problem with Wiener covariance structure is all that we need to solve the original problem with any product covariance structure. Consequences. Any design problem with the product covariance function is in some sense equivalent to a design problem with the Wiener covariance function. So we have a design problem with the product covariance function, we transform it to the Wiener case and do everything in the Wiener case. Hence, we can focus on the design problems with the Wiener covariance function, which can be taken as canonical, in some sense canonical for all product covariance function. To solve the design problems for all product structures, it's enough to use the Wiener covariance structure. And for this Wiener model with F, the formulas, for example, the formula for the information is the following, very simple. Well, it looks simple, it's not that simple. In our attempt to maximize M, we need to maximize this function essentially. This will be fixed, of course. We need regular designs. We work with regular designs with fixed initial point T1, but to maximize this is not completely trivial. It's not that difficult either, but it's not completely trivial. We can do it for some special classes of these functions f. No, assume that we have a design, fixed design tau. What happens if we add a design point t plus between 2 points, say tk and tk plus 1? That is a very natural question. So we have a design and we add an observation between 2 points tk and tk plus 1. So the formula for the difference between information of the added design of the design that is enriched by the additional point t tau plus minus the original information for the design without this point t plus can be written in the following form. I intentionally selected this form between many other forms that are possible because it tells us immediately, firstly, that by adding this new point, we cannot decrease the information. This seems to be trivial, but it's not completely trivial. In these correlated models, all kinds of strange phenomena can occur, of course, so we must be very careful. But this is not the case. Simply adding a new observation cannot decrease the information. The information might stay the same sometimes, but it cannot decrease the information. And then, for example, from this formula, we see immediately, taking into account some analytic assumptions about the function f, that if we move with the edit point to the tk point, to the left, then the information decreases to the m tau, and if we move the edit point to the right hand side neighbor, then the information goes again to this original information m tau. So it behaves very, very nicely, no problems. And we might ask, when does this information stays the same after adding the point t plus to the design? Can that happen? Yes, it can happen. And this formula is again leads to geometric understanding when this happens. If you look closely at this determinant here, it might be 0, that is, the difference might be 0, only in the case that the three vectors tk ftk, t plus ft plus, and tk plus 1 ftk plus 1 lie on the common line. Okay, so if we have measurements in tk plus 1 and anywhere else, and if we add a measurement in t plus, and if coincidentally, if it happens that this point lies on the same line as these 2 points, then we will add no information. The information will stay the same. So a theorem is that we can assume the model, the Wiener model on the experimental domain t down, t up. Then there exists an optimal endpoint regular design. It follows from the consideration before, after some technical details. And if f is not linear on any interval under t down, t up, then the function of the informations for adding points are increasing function of n, so they do not stay the same. The informations for consecutively optimal designs increase. They increase up to some level, not infinity, up to some finite level usually. And using Wiener equivalence theorem, we can formulate the same for any model with product covariance functions. Then we would not require that the function f is linear, that we would require that this seemingly complicated function, but we can evaluate it, no problem, is not linear on any interval a, b under t down, t up. Let us look at the classes which permit simple exact optimal designs. The first is the class of quadratic functions, the parabolic class. A0, A1, and A2 are given functions, any given functions, such that not all of them are 0, of course, so that we do not have the 0 function here. Then the optimal endpoint regular design for this model, for the model with Wiener covariance structure, as I said, we can focus only on the Wiener covariance structure, is simply the design that forms arithmetic progression. So the equidistant design is the optimal one, exactly optimal one for this class of functions. Secondly, let us assume so-called square root class of regression functions. That is very similar as the one before, but instead of t squared, we have the square root of t. Then, surprisingly enough, the exactly optimal design is the one, the points of which form a geometric progression. So it's not equidistant anymore, but it is in some sense, it is equidistant. It forms a geometric progression. And from this result, we can use the Wiener equivalence theorem to say something about all other covariance structures. So for example, let us look what we would obtain if we use the Wiener equivalence theorem for the Ornstein-Uhlenbeck covariance function. And we would obtain the following. If ft has this form, keep in mind that this can be 0 and this can be 0. Simply it can be a constant, an unknown constant, or 1, for example. Ft can be 1, it's still not so trivial. Then the optimal endpoint regular design for this model with Ornstein-Uhlenbeck covariance structure is equidistant. And this is something that was already known in several papers, for example, in paper of Milan and Joseph in Statistic and Probable Letters. So essentially this theorem about the square root class using the Wiener equivalence theorem is the same as the theorem about optimality of equidistant designs for the Ornstein-Uhlenbeck covariance structure. And thirdly, if we have the function, the mean value function or the regression function of this form, where again C0, C1 and C2 are some constants, not all of them 1, then the optimal design is the one that forms the points of which form a harmonic progression. Surprisingly, now it's harmonic progression. Again, we can use this Wiener equivalence theorem to get all kinds of results for all kinds of product covariance structures. I will skip this. What I call optimal nested designs, or nested designs. Assume that we have function h from the experimental domain to 0, 1, such that the inverse of 0 is t, and the inverse of 1 is t down, and inverse of 1 is t up. And this would be the optimal endpoint design of the nested type if it can be written in the following form. This is the same procedure as is used for constructing asymptotic designs. But we require that this procedure gives us exact designs at each step. That is, this is the 3-point design based on the function h, or perhaps I should use this. And this is the 5-point design based on function h, okay, these points. What is remarkable about these designs, or what can be used? Very simple, is to note that the middle point stays the same. If we go from a 3-point design to 5-point design, then the middle point, of course, stays the same, okay? And this allowed me to find these 3 classes of mean value functions. How? Simply, I tried several functions f and numerically constructed 3-point and 5-point optimal designs. And then I checked whether the middle points in this 3-point and 5-point design coincide. If they do not coincide, then these designs cannot be that nice, they cannot be nested, whatever the function h. I do not require knowledge of the function h. Simply, whatever h, the middle points must be the same for 3-point and 5-point optimal design. So, by doing this, I found these 3 classes of designs, and there's some conjecture that I won't go into details, that these 3 classes are the only 3 classes that lead to these nested sequences of optimal designs for the Wiener covariance structure. Ultimate efficiency. For a model F with Wiener covariance structure, let tau and star be the endpoint optimal regular design. By the ultimate efficiency of a regular design tau on this experimental domain with any number of design points, so tau can have any number of design points, we mean m divided by the limit of the informations of the optimum designs, with n goes to infinity. The value of this limit is something that we can call the maximum possible information about beta that can be gained from an observation of the process, from observation of the full trajectory of the process, essentially. It is typical for the models with correlated observations that the maximum possible information is finite. That is, even knowing the full trajectory of the process, we cannot estimate beta with 0 variance. It has long been known this. But this is finite. So if we calculate this ratio, this gives us something like an efficiency not within the class of endpoint designs, but within the class of all designs. Ultimate efficiency. Nothing can perform, if this would be 90%, then nothing could perform better than 110% better, so to say, than our design with any number of design points. It turns out that for all three classes of regression functions, the ultimate efficiency of the endpoint optimal regular design tends to be very high, even for small numbers and of observations. This was also plotted on some picture at one nice talk yesterday, I don't remember, the same observation, that even for a small number of points, you already obtain a very high efficiency as far as estimation of the parameter is concerned. So here we have pictures. So for example, I selected some of these functions from the classes, from the parabolic class, square root class, and hyperbolic class, and these are the ultimate efficiencies. So for instance, with 4 points, let us look at just 4 points. The 4-point optimal design is at least 94% efficient with respect to any design with any number of design points, even 1,000 design points. So it's questionable whether it's worthwhile to do more experiments than, for example, 4, okay? Because we wouldn't obtain much more information even with 1,000 points, only a very little gain in information. And for these two functions, mean value functions, it's even better or worse, depends on the point of view, okay? So the efficiency is already very, very high with, say, 4 or 5 design points. Very good. So I'll skip the multivariate case and go straight to conclusions. Product covariance functions form an infinite class of covariance functions covering the covariance function of the Wiener process, the Ornstein-Uhlenbeck process, and the Brownian bridge as special cases. The optimal design problems with the product covariance function can be transformed one into another using the Wiener equivalence theorem. So it's enough to solve everything for the Wiener case as far as product covariance functions are concerned. For the Wiener covariance function, and particularly the parabolic, square root, and hyperbolic classes of regression functions, we can construct exact optimal designs that form the points of which form arithmetic, geometric, and harmonic progressions, respectively. It seems that these classes of regression functions are the only one that lead to these nice designs that I called nested. The information provided by the optimal endpoint designs approaches the maximum achievable value very rapidly. It's usually very rapidly. That is, there is no need to perform more than several observations to estimate the parameter beta. Thank you for your attention.
Questions? What about uniqueness of optimal designs? Because they're obviously not unique.
Yes, I haven't proved that theorem about uniqueness. You're completely right. This is not so simple.
No, I can prove theorem that they're not unique because all your designs, if the third coefficient is 0, yes, they're all optimal.
Okay,
according
well,
to your theorem.
Then that's good that I told that I haven't proved the theorem about uniqueness. Because it's not valid, okay.
Maybe, very nice talk. Maybe it will be nice to relate to the results in stochastic processes. People like students of the Chorgo, they proved around 10 years ago that you can reparameterize monotonically from Wiener process Ornstein-Uhlenbeck in 1D, 2D.
It might be related to this.
Yes. Given by this reparameterization of the.
Yes.
Because it's just a very monotonic. It's exponential reparameterization.
Yes. Thank you. Look at it.
So 2 points. I think I mentioned this morning about time dilation. So this corresponds to a time dilation, doesn't it? This transformation.
It's something like a time dilation. Yes.
The other question is, what about fractional Brownian motion? Does it not fall in this class?
I don't think so. I'm not sure. Has someone?
No, it doesn't have
product multiple.
Yes. It doesn't have a product form.
So it's not possible.
Yes.
Yes.
So your processes, as far as I understand, are Markovian processes, right? But there are some conditional Markov and Gaussian processes,
Yes.
where you can condition on initial value and you get the same structure. So it's more general. I don't know, kind of more general. So did you try to do the same?
Just what about?
Because you can have increments of linear process, for example, as a process, and some other.
I haven't tried it yet. Now I will have 5 months.
Say,
You're welcome, Jay.
It's very nice.
Okay, so thank you very much once again.